Good morning and welcome to this short presentation about the Digital Future Demonstrator project, Susan's Ride on Campus 2030. Susan's Ride on Campus is about sustainable smart road infrastructures. My name is Jordan. I'm Professor of Teletraffic Systems at the Division of Network and Systems Engineering at KTH. The project team consists of faculty and students at 3 schools of KTH, myself and Raksha Ramakrishna, postdoc, at the School of Electrical Engineering and Computer Science, Yuki Shao, a master thesis student, Nicole Kringos, professor at the School of Architecture and Built Environment at KTH, and Martin Törngren, professor at the School of Industrial Engineering and Management at KTH. The motivation for the project is that road construction today is highly non-optimized, which leads to rutting, cracks, and potholes in the road infrastructure. These, in turn, can harm traffic safety and lead to increased road maintenance needs. Now, road maintenance today is highly reactive and is actually fairly expensive. Between $1,000 to $20,000 per kilometer per year is the cost of road maintenance on average. Now, we argue that data could be collected and used both during construction and during operation of the road, which could decrease the road maintenance costs on the long term. With this in mind, our objective is to demonstrate the potential impact that digitalization could have on road construction, operation, and maintenance. We want to show the potential of data-driven construction, operation, and predictive maintenance, and we want to identify and work on the lacking systemic structures. Our project focuses on 3 phases of the life cycle of road infrastructures, starting with decision support during road construction, using the information that we learn about the road for predictive maintenance, and also using the information that we have about the infrastructure for influencing traffic behavior on the road infrastructure with the intention to increase the lifetime of the road infrastructure itself. At the heart of the project lie digital twins that consist of models of the road infrastructure and of the vehicles, and data that are collected and are used for prediction and learning, both in real time and on the long term. We aim to demonstrate these results in 3 use cases. First, focusing on real-time feedback to the operator during road construction. Second, through showing by simulations how predictive road maintenance could decrease the road maintenance costs on the long term. And third, through showing how autonomous vehicle behavior could be adapted to the road infrastructure conditions. To give you examples, I will first focus on smart compaction, so road construction. Now, let's consider the construction of a certain section of a road and divide this section of the road into a number of slices. Assume that these slices are homogeneous. There are a number of models that can be used to model how the road infrastructure would react to compaction. These are so-called finite element models of the road infrastructure. One example is the viscoelastic Berger model. This model has a number of parameters, and using these parameters and given a certain loading, that is a force, and the duration during which the infrastructure is exposed to this loading, it tells what deformation the asphalt, that is the roadbed, will suffer. Now, how can we use this model? Basically, the problem that we address is the following. When we start the compaction, we have a prior belief about the parameters of the asphalt that we are about to compact. Our actions consist of the loading and the duration that we will expose each section, each slice of this road section. During compaction, we make a number of observations. These observations are the deformations that are caused by the loading and the duration of this loading combined with the actual parameters of the roadbed. And our objective is to learn basically the parameters of this roadbed through the interaction with the roadbed in an iterative online manner. And for solving this problem, we propose to use approximate Bayesian computation. To give you a high-level idea, it works the following way. We have an initial belief about the parameters of the roadbed. We use this belief for choosing the loading and the duration for the next slice of the roadbed. We observe the deformation. We use the deformation that we observe to update our belief about the parameters of the roadbed. And then we use this updated belief for choosing the next parameters for the next slice of the roadbed. To give you an example of how one could adapt the operation of autonomous vehicles to the infrastructure conditions, we developed a demonstrator that combines information from Trafikverket, the Swedish road administration, and information about the weather, about the environment into a digital twin, a database, and uses this to influence the route planning of an autonomous vehicle with the objective to avoid obstacles in the roadbed. Here I show you an example of how this works. On the left-hand side, you see data that are stored in the database. This information is gathered from Trafikverket and other sources and is read into memory in real time. And during route planning, the vehicle will use this information to actually change its path, as you can see in the video on the right. Beyond these, we have ongoing work on smart compaction, where we are working on a simulation-based demonstration of compaction, and we plan to calibrate our simulations using real-world compaction data obtained from our industrial partners. And we plan to simulate and visualize the predictive model of wear and tear of the road infrastructure. In the area of infrastructure-aware autonomous vehicle path planning, we plan to visualize how the path planning is affected by the road information, and we plan to implement a simulated demonstrator on KTH Valhalla-Wegen, that is on the KTH campus. Overall, our project paves the way to sustainability through reducing the carbon footprint of the road infrastructure construction and maintenance. We plan to achieve or hope to achieve a 95% cost saving if the cracks are detected early on, timely. And we hope to achieve improved traffic efficiency, better safety, and more economic and social sustainability. I would like to thank you for your attention. And if you would like to have more information on our projects, I invite you to visit the project homepages following these links.